All right, I think we can get started. Good afternoon, everyone. Welcome to the Data Science Seminar from the University of Washington eScience Institute. I'm happy you're here with us despite the nice weather outside. It is my pleasure to host Dr. Marine Denolle today. Marine earned her PhD in geophysics at Stanford University after completing master's and bachelor degrees at École Normale Supérieure in Paris. She's interested in studying Earth's structure and quakes dynamics using large-scale computing of seismic data. Marine, today we'll talk about data mining the Earth's vibrations. Please do not hesitate to use the Q&A button at the bottom of the screen to ask questions during and after the seminar. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes within the Suquamish, Tulalip, and Muckleshoot nations. And with that, Marine, please take it away. Thank you.
Thank you so much, Nicoleta. So thank you so much for coming here despite the nice weather that we finally got. But I think I'm going to show you that we have some exciting, new, diverse way of thinking about Earth systems. And so today I wanted to talk to you about how we data mine in my group, the Earth vibration. And by vibration, I mean literally ground vibrations. And this is work that is done in great part at UW with undergraduates, graduate students, and postdocs. And I also have some history from a previous students at Harvard where I was a faculty too. But a lot of it is enabled by eScience. I want to give credit to eScience as we go along. All right, so you might think about a seismometer that could look like this. And I hope I'll give you a more modern version of this. But this is some of the original analog seismometers that were deployed. One of them was deployed at Mount Rainier for a very long time. And the needle is moving, the tube is rotating. And then when we have an earthquake, you can see the vibrations that show like this. So this was back then what seismometers look like. Nowadays, there's a more diverse pool of instrumentation. They're sensitive to different seismic frequencies. I own one of these called Meridian. These are the seismic network STS2, really high quality data. We have some more cheaper ones that actually have very good and easier to deploy. Oceans are sensed as well at the bottom with these elaborate, super expensive equipment. And then more recently, people have been using optical fibers to sense, distributed sensing. But this breadth of sensing instruments allow us to really look at different aspects, spatial scales and end scale in Earth processes. One day of seismic data may look like this, and I pulled this out at the PNSN website where they display one of the seismic stations. It's on Mount Rainier. And so the x-axis is minutes, the y-axis is every 30 minutes or 20 minutes of the recording. And you can see up and down in this time series, some very impulsive, some very low frequency. And really what we're trying to do as a seismologist, I look at this data and I'm trying to get as much Earth information about the Earth as possible. From there, I can see from my kind of junior experience that this is a strong distant earthquake, very well separated phases, some P wave and S wave. They're separated, meaning they are very far. If they're very far, they must be large, otherwise we would not see them on the seismogram. But there's also a very interesting signal here, like maybe this low frequency could be some kind of wind excitation. All of these bumps here might be earthquakes. The PNSN only had 2 earthquakes that day. So you can see there's a lot more in the data that maybe we can tell. Just to get some scenery, because we're in the Pacific Northwest, this is the Camp Muir station in Mount Rainier that is being serviced by the USGS. And so it is possible as well that we see climbers on these kind of data. So we can actually sense human motion and anthropogenic activities in these seismometers. The goal of that station was mostly to monitor the volcano, but what I'm trying to say, there's a lot more in it. If we move to a station that's close to the coast, it would look more like this. This is a station in Forks. And I'm sure many of you have been on the west coast of the Olympic Peninsula. It is weathered. It's a very intense weather station. It's close to the coast. The ocean there, it's not Southern California. It's not Brittany in France with like nice little beach, sand and quiet sea. This is really active ocean. And the action of the waves actually on the shore and on the seafloor actually excite a lot of seismic waves that you can see on these seismometers. So these seismometer, and I can tell from these wiggly waveforms here, very loud, are very likely the action of the ocean on the solid Earth. And we can extract a lot of information, both from studying the ocean, atmospheric processes, but also use these waves to understand Earth processes. That's kind of what I want to show you today. Is from these seismometers, shown with this old school one, we can understand a vast range of processes. They can be natural hazards like volcanoes, tornadoes, large storms. We can see the trains, we can see the cars. We can feel very interesting anthropogenic activities in wind farms. We can hear elephants. We can hear all kinds of animals and whales from these seismometers. And the type of data that we extract has different characteristics in their signature in the seismogram. We may have some harmonic signals. Often these anthropogenic signals give some harmonics. We can have some diffuse field. This is a complex Earth, maybe complex process will give us a very diffuse aspect. And then we can have some transients, and that is more typical of the earthquakes or volcanoes. Here I moved here a couple of years ago now, and this is a very dynamic system, and we live here. This is almost the main reason why I moved here, besides being close to eScience and doing lots of research. But if we take a view of the Pacific Northwest, what really got me excited, there's a lot of things going on. This is such a neat natural laboratory to study the oceans, to study tectonics. We have this active subduction zone on the West Coast. It does not produce too many earthquakes. That's good for us. We have tall buildings like the Space Needle, which are infrastructure that can be susceptible to shaking. Lots of volcanoes. We have glaciers. It's just a very dynamic system. And so what I really like is basically use seismic data to discover phenomena within these processes. So first, we'll talk about how we discover events. And I want to be very generic, not too generic. We'll think about natural systems. But the first thing we did when we moved here is to think about earthquakes waveforms. And moved here 2 years ago, the first thing that first grad student at UW is doing, and he actually gave a talk a couple of weeks ago at the eScience Incubator. He's really strong. Is we just started from any basic data science project is to look at the data and curate the data, which is a really understated part of any machine learning or data science workflow, is really preparing a rich data set. And in exploring the data that PNSN, Pacific Northwest Seismic Network, has collected over the past, we only used 20 years, but it has been recording for 50 years or so, not continuously. We looked at this map here of the location of the earthquakes that happened, and we're recording by the PNSN. You probably didn't feel that many earthquakes, but there are a lot of tiny earthquakes. This is correlated with depth. So around here, we tend to have like deeper earthquakes. There's a lot of shallow seismicity next to the volcanoes, but it's a pretty rich place if you care about small earthquakes. And to the right, we see the state of the seismic network. It's grown tremendously in the past 5 years to satisfy, with the goal of an earthquake early warning system. The size of the triangles is just a number of waveforms that we have from that data set. So bear in mind, like this is 10,000 waveforms per sensor. But you can see we have a lot of sensors in Puget Sound, lots of the volcanoes, Mount St. Helens, Mount Rainier. This is the national labs with nice nuclear waste monitoring activities. And so what we did in collecting this data is really look at the long-term history of the network, looking at biases in the labels and the attributes that we had based on the history of the seismic data. So it's been a really a pleasure to have a deep dive into the history of seismicity in this region. In doing so, we collected about clean data. So at clean, it's quite an objective attributes, but we collected about data for about 50 or 45,000 events on as many stations as we could, maybe like 5 to 10 to maybe 20 per earthquakes. And I'll show you a little bit about what we think about is we have earthquake of magnitudes from 0 to 5. You will feel the 5. We haven't had that many 5. in recent years, most of them occur actually offshore. We have more and more small events. So this is number of events in log scale. And this is typical of earthquake seismicity everywhere on Earth, is that you have a lot more of these smaller events than you have of the large events. It's actually a very nice parallel of decay. The type of attributes that we want from earthquakes is the arrival time of the waves. We care about P wave, premier, P wave compression, shown in blue here as labeled as the most impulsive part of the waveform when the shaking arrives. And then the S wave, which is the shear wave, slightly slower wave that arrives after. And then here I'm showing you two examples of real data, clean earthquake waveforms, low noise, high signal, and what it is actually in real life when you actually look at all the stations that are coastal or something like that. But the network, actually, the analysts at the network pick these arrival times, and this is our labeled data. This is what we're going to use to locate earthquake later on, and sometimes to even compare the type of events that we have. And so this is mostly data from the seismic network that we collected ahead of developing more sophisticated methods for earthquake catalogs. The features of the earthquake waveforms are quite common to most earthquake, is that they're very impulsive seismograms. So I'll show you an example here, a kind of a raw seismogram, maybe a bandpass filter seismogram. And because earthquake seismograms are impulsive, the most basic earthquake detection workflow is to compare the amplitude of a short-term average, shown here, maybe a long-term average amplitude over 10 seconds. And when you make the ratio of the two, it is literally just an impulsivity filter. It's a filter that will tell you how impulsive the waveform is with respect to two different time scales, short-term, long-term, tunable, as you can tell, like these are parameters that might be tuned. But anyway, this filter, this feature of the data is sufficient to detect earthquake. It misses events that are buried in nodes and whatnot. But this was proposed by Allen in 1978, and it is the one impulsivity filter that extracts features from seismic data that is used by seismic network. Actually, know very few that would have more sophisticated way of measuring data. This is really the standard way of detecting earthquakes. Other types of events are they're more complicated, they're less impulsive, and therefore they tend to be missed and disregarded, in part because the seismic network's mission is to talk about earthquakes and warn about the shaking hazards that will come. But there's actually a lot of other things that were picked during these 20 years that do not really look like earthquakes. So seismic analysts don't really know what to do with them, besides saying like, hey, something happened, it's transient, and it could be interesting. And at the network, they labeled it when they knew. So for instance, what they call so from the earthquake perspective, explosion, quarry, blast, or not are standards in the earthquake catalog. Earthquakes are standard, and we have a lot more of these labeled data than we have others. But what I'm trying to do here is actually expand on knowledge on these other type of events. Pardon, this is a little bit limited type of label, fortunately, but we have other things like sonic boom, which are from thunderstorms. Some people call that thunderquakes, but also you may have meteorites shooting that may trigger sound, or even think you can have acoustic signals from gunshots. This is probably why you see a lot of these showing on the east side. We have thunder. So thunder is showing here. Thunderstorms, you hear the sound, it wakes you up at night. Well, that sound transmit waves in the subsurface, and subsequently the seismograms will pick them up. And so I'll show you a few examples. So here we have, I think that's a sonic boom here, and multiple shots that you can see. And then on the right side, we have this other wave that's more emergent and then decays. It's quite long, over 20 seconds. And these are what they labeled as surface events. And when we count the number of seismograms that were picked at the seismic station, the surface events tend to occur in mountainous regions, and then some of these, some thunder and sonic booms are more distributed. But what that tells you is there is a focus of these processes that happen in a mountainous region, and this is a likely association with avalanches and landslides and whatnot. But at this point, we don't know. We just have very few labels from climbers telling there was a rock fall, there was an avalanche. The rest is just from the network perspective, just saying, this is like a surface event. So part of my research goal in our group is to say, what are these and what they are. Another interesting aspect to motivate our investigation on these surface events is these kind of surface mass wasting events are really damaging. They're more distributed, they happen, they're weather related, but I just wanted to stress that this type of events cause a lot of damage in great part actually in Europe, but even on the West Coast. And we saw a few examples this past winter with a lot of rain events, lots of debris flows. These are fast mud flows. You can see a photo here. So it's basically a very thick river that burst or river that transport a lot of rocks. And let me go back here. Lots of big boulders that can cause a lot of damage. And the seismogram from this, so they're very loud. You can hear them. You can feel them with the seismograms. They have interesting time frequency representations that are of active investigation in the Alps, because the Alps have a lot more exposure to mountainous regions and avalanches. So this paper came out with a simple random forest to pick out, discriminate between an incoming debris flow, an ongoing debris flow, and what was noise. And what they did in this study is really extract features from the data using statistical and kind of physics-based feature from that seismogram. But in general, these debris flows and landslide have this emergent, non-impulsive, so they don't get picked the same way as earthquakes, tend to have somewhat a higher frequency than earthquakes and long duration signals. In the United States, these kind of mass wasting events kill about 20 to 50 people per year. And so it's not as flashy as an earthquake, and that would cause a lot of damage, but it's this continuous hazard that occur over time. There was, of course, the 2014 also landslide that the Pacific Northwest is still remembering. At the larger scale, the debris flows can become lahars. And lahars is an Indonesian word to basically a mud flow from a volcano. So here I'm showing a pretty drastic view of what a lahar is after the 1980 Mount St. Helens eruption. We don't have seismic data for these because the data then was only recording earthquakes. But what you can see from these mud flows, they're giant, basically lahars are giant debris flows on volcanoes. They're actually the biggest hazard in the Pacific Northwest from the volcanoes. And so the USGS is investing in instrumenting using geophysical sensors around these volcanoes. The damage about these, unlike debris flows that tend to be somewhat local, is they go very far. And I think some of the Puget Sound is sitting on debris flows from Mount Rainier's lahars. And so these tend to be moving at speeds of like meters per second, tens of meters per second. It can be kind of fast. But there's enough distance that warning is possible for these events. Anyway, this could happen to Mount Rainier. And so part of me being here is this excitement of trying to understand these processes so we can better predict and forecast when they occur. So we have waveforms. There's no automatic way to study them, so they're pretty picked. And we're going to try to understand where they are and what they are. So if we'll start with where, I worked with two awesome undergrad students. Francesca is from UW, and we did some basic seismology with her. She started from the ground up, learned Python, and within a year, we got some really neat results. I was very excited. We looked at these weird surface events. Some of them were picked by the PNSN. And this is an example on Mount Rainier. We'll look at the seismogram. The up and downs are the vertical motion of the ground. This thing occurs over 15, 20 seconds. And you can see here the envelope is, emergent and down. And they seem to have different arrival times at different stations. And because we have different stations looking at this map here, and different arrival time, we can actually use the difference in arrival times to locate them. So the center of this arrow here is showing you what our very crude first order seismology 101 location would give us. Another thing we did that was kind of fun is if you remember the sound of a police car, an ambulance that comes to you and goes away, there's this high pitch sound when it comes toward you and low pitch sound when it leaves, called a Doppler effect. So it changes and stretches the frequency content of that sound. Same thing for earthquakes, actually. When an earthquake ruptures, and goes unilaterally somewhere in one direction, the waves ahead of the rupture will be high pitch, high frequency, and be low frequency behind. And we can't really apply this technique per se on these type of waveforms because these are very emergent and complex signal. But what we did is, crudely speaking, let's take the full waveform and do the same exercise and looking at the spectral content and seeing if there is a difference between azimuth and whether or not some azimuth have more high frequency or not. And from that, we're just guessing that these are flows going down, hopefully down in our collocation, that the direction of the flow will be telling us about the direction of the landslide. It's a very crude thing, and we're still in the process of ingesting of that data and verifying, but these arrows are showing you that, at least for that event, we think that this was going downhill. There are instances where it goes uphill, which indicates that we have some problems there, but that's part of the fun of exploring data. So then Francisca located all these events, and you see these maps of Mount Rainier, Mount St. Helens, Mount Hood, the density of the number of events reflect the density of the seismic network. So there's a strong bias there. But nonetheless, you can see that using stations around, which are not shown here, but we can locate the events being mostly on the top, from Mount Rainier being kind of northeast. And I know a lot of people climb it from the south, which makes me think maybe it was a safer route because there are fewer avalanches. Mount St. Helens, everything is in the crater and on the outside, so that seems to be quite normal given the active survey, and Mount Hood were kind of out of luck, potentially a bad station distribution. But anyway, that was kind of an interesting piece of work. We have other ways to look at the data, and I want to give a good credit to eScience for running these incubator projects. And there's this detection algorithm called RedPie that was part of Alicia Hodovec's eScience incubator in 2014, which basically create a catalog, detect automatically like what any other earthquake seismic network would do. And then it uses that waveform and say, hey, I'm sure this repeats in time if the earthquake is located at the same spot. And so it uses the idea that earthquakes can repeat in time, so they have the same fingerprint to then go back and data mine with kind of knowledge and supervised learning, data mine the rest of the data, of the continuous data. And so we're trying to expand and learn from this catalog that's been running since 2014. And we're using, again, with another super savvy next undergraduate student, really cool, running on GPU after a month of starting learning Python. It was really impressive. What we looked at is we created kind of templates and fingerprints for this data, about 30,000 of them. We're using a lot more seismic stations. We're using 5 volcanoes. We're exploring how they repeat. And it's work in progress. It's very long to analyze, but Nick was able to locate these events also within the volcano. Part of them are volcanic. Part of them may be surface events. We actually don't quite know what they are. We're also trying to repeat this data, detection, re-data mining of the data by using all these templates and fingerprints. And it's a lot of cross correlations. So despite using GPUs, these things still take a lot of time. But this is the biggest cross correlation job I think my group has been running. And then the other thing that we're trying to explore is how diverse these type of events are based on the waveform characteristics. And so now we're trying to use unsupervised learning techniques, looking at features of the data, either in time domain or frequency domain or both, and doing clustering to find if we can discriminate between, these kind of surface events from these earthquakes. And so it's ongoing work, and to the first order, we're not able to do it using time domain clustering, but I think our time frequency work is showing that it will be able to discriminate between these types of events. Quite fun, and we hope to get some results soon. So what are they? Because we have these waveforms, I didn't tell you what they are yet. It's very hard to know. But for that, we're using a small but ground truth data set that's globally collected by a former student from UW, and in part with some of the faculty here, called the Exotic Events Catalog. And there the data is curated, clean, ground truth with satellite imagery to really say what these events are. So the source types now can be snow avalanche, rock or ice, or rock and ice, debris or avalanche and slide. There's a lot of jargon and kind of description of these processes that make it actually kind of hard to classify. But anyway, these are very nicely collected everywhere in the world that we have seismometers and seismologists typically. So I'll show you an example. This is work done by Akash Karida, who's also a grad student here. What I want to try and do is learn from that data set, extract the features and understand what feature is most discriminatory for these different types of events, and then return back to the Pacific Northwest and try to separate the event types within our data. So Akash is an interesting problem of we can extract features from the data and we can predict, we can do a regression model to predict the size, or we can do a classification and predict what type of events they are. And so it's interesting to actually think about, we think about features, but we don't necessarily think about the problem that we're asking. And so what I'm trying to understand is, given the different types of questions, a regression problem or a classification problem, what type of feature will become more or less important? Which ones will be telling you about the type of processes? Which ones will be telling you about the size? And these might be different answers. And I like to tie, the type of machine learning workflow we do in thinking about the question and the data that we're using. So we're doing a lot of these. This is a rockfall event. We're doing a lot of these time frequency representation, envelopes, duration, all kinds of measurements. And the first answer that we had with these kind of engineered features based learning is it's a mess. It's very hard to discriminate between the two. So it seems like to the first order, our typical kind of like engineered feature extraction may be insufficient in separating the types. And it's a nice way to motivate the next step, which might be more a deep learning type approach to extracting features if the standard ones are not working. So hopefully we'll get to work on that. Okay, I'm gonna jump quickly there because I'm spending enough time. Another thing we're trying to do is like to highlight a good group is Shibin. She's a postdoc in our group, and we've looked at noisy events. So if I go back actually in these waveforms or others, we can see that there's a lot of noise sometimes in the data, and when we extract features, there are sometimes feature of the noise that comes out. And we really want to say, like, I really want to get just to the earthquake or just to the surface event. And I don't want to use the noise. I want the noise to be removed if possible. So one way to do that is to separate them. And so we're using this kind of a multitask machine learning model. So if you look at the core here, we're doing some kind of transfer learning from previous grad students' work where we take on the data as time series and we enter this into an encoder decoder with two branches. One will say, make sure that we reconstruct the noise correctly. And the other one will say, make sure we reconstruct the earthquake signal correctly. So now we're taking this supervised approach to really try to separate the types of wave field. And in a way, it is separating wave field characteristics. So one that would be more of a diffuse time series, this ocean noise at that Fork station, it's something that's hiding a lot of earthquake signals in them. And the other one is saying, I really want to get to reconstruct the actual earthquake waveforms. And so in doing so, we are doing denoising of earthquakes. So these are smallish earthquakes, deep earthquakes, showing you time series from seismogram before and after we do denoising. And that allows us to do a lot more investigation of smaller earthquakes that would not be studied otherwise because they're buried in noise. And so that really opened much bigger data sets to understand earthquake processes by just putting this denoising as kind of like a part of a pre-processing, nothing fancy, just saying like, once you've separated the signal, now you can actually do science. And I really like this idea of enabling science using these models and not as using these models as the goal. So I like the idea of where could that be actually part of our generic pipeline. Let me skip on the ensemble learning, the more complicated. I wanted to speak a little bit about, we have these events, but we also have the noise, and there's a lot of information that we can extract from the seismic ambient vibrations. It's actually something I started in 2008, not that long ago, I would say. But what we started doing is saying, okay, if we were not the first, but I took that type of research to a different directions than most of the community, more interested in predicting earthquake shaking. But let me cast you the concept of the approach. We have 2 seismic stations. This is cartoon geophysics, nothing complicated. We have waves that bounce in the Earth's subsurface. Some wave is gonna go from my station A in Forks to my station B in Mount Rainier. And they both record something that looks like something you would disregard as any earthquake scientist. That's why seismic networks did not include this before. But this diffuse field actually records a weak wave, low amplitude wave that goes from there to there. It happens that if you do a cross correlation between these 2 noise time series, you may actually reconstruct the type of wave that will go from A to B. You can actually enhance the signals from that. What's interesting in terms of a computational aspect of this research is we do this operation every minute, every hour of time, and then we pair sensors. So there's an interesting scaling here that we do this operation every minute, so we're independent in time, and then we tend to stack things. And so it's linear in the duration of the record, which is nice for cloud computing. But we also pair sensors. And so pairing sensors is fine with the traditional seismology where you had 10 sensors, maybe 100 sensors. But as we move to growing seismic network, this n-squared problem is becoming challenging. And so in computationally, we are working a lot, and still today, thanks to eScience, in having good workflows that will distribute, will leverage the infrastructure to do this computing at scale. The data of this correlation may look like this. It's 2-sided, where you imagine this as kind of an earthquake signal. And then we can repeat this every day, every year, for many years. This is an example of a Pasadena area, San Gabriel Valley in California. There's Caltech there, so they had lots of good data, continuous data since 1999 and before that. And for this this pair of stations, we can see this wave, virtual wave, so red and blue are up and down, shaking. You can see that it's pretty stable over time. And so that same wave in 2000, for the same station pair, the same path between Rio in the central of the valley and NWCS on top of the San Gabriel, the wave would arrive at the same time, which means like if there was an earthquake in 2002 at Rio and it's recording MWC, it would look the same as an earthquake that happened in 2016 between the same station. So that's good. What we found though, is the subtle changes in the Earth's subsurface can be seen in the late part of this wave. So the first wave arrived, that's your shaking, that's your hazard. And after that, shaking, goes down progressively. And these waves in the back, are not dangerous for shaking, but they actually sense the Earth very well. And so they actually have a lot of information about the Earth structure that we're tracking. We've developed this large-scale computing for using Julia for this kind of workflow. We do a lot of data manipulation. This was with Tim. We developed the full ecosystem, not the full. We developed the first ecosystem for seismology in Julia. It's hard to pick up because adoption is taking time. But anyway, we do a lot of data manipulation. We reshape data, we Fourier transform data, we correlate data. And then we can do this at scale in a very efficient way. So Tim has been able to run on one AWS instance for one day, 90 terabytes of data with these cross correlations. It's been really cool to enable this in like a small compact job. And so we did this a lot for California. We looked at 20 years of data and looked at how the Earth may change in the slate coda over time. So what I'm showing here is these dots. These are each station that we're looking in Central California. we have years here, so 20 years worth of data. And you can see these time series are showing you ups and down, ups and down. These are the features that we extracted from these waves, measured every day, and we're looking at how these changed in time. This is actually the velocity of the Earth structure changing in time. Now you can see there's a lot of up and down, and then this blue curve, Nicoletta, you might like this. This is the liquid water equivalent data product from GRACE. And you can see these nice correlations, seasonal correlations between, a rain events in California that was 2005 and this year, which we don't have here. So lots of rain that would reduce the seismic velocities of the wave speed of the sound waves. And then long-term droughts in California where you have no rain for a long time. And as in drying the soil, you actually increase the seismic velocities over the course of 20 years or so. And we found that lower water levels induced a lot, it seems like a lot, statistically a lot of higher seismic velocities over the course of 20 years. So +1 to 3%, it's a large under prediction because we have low sensitivity to these measurements, but still, it's been interesting to look at this decadal change because this is information that can be used for predicting seismic hazard. Now I'm sure that this was reset this past winter, but the paper came out in January. But if we were to analyze data today, I'm sure we have a reset / maybe lower velocity today due to the very intense winter that California had. We did this in Mexico City as well, way fewer stations, but we had 25 years from a French geoscope array. This is work that was done with Laura Ermert, who's also a postdoc here. And what's cool about, it's not really cool, but what's dramatic about Mexico City is it used to be a volcanic lake that's been drained to be used as, for urbanization and for agriculture. And in pumping the groundwater over the course of 100 years, Mexico City has sunk by 10 meters or more. Today, the rate of sinking, it's uneven in the basin, but it's about losing elevation of 1 meter every other year. It's really dramatic. You can see that for these old cities that have been urbanized over 100 years ago, there is an uneven subsidence in the basin, which creates this wavy-like floors for this city. So it's really dramatic. The other thing about Mexico is it does have a lot of earthquakes and volcanoes. And because of that, there was actually very strong shaking that happened during earthquakes. It's sediments, and so waves tend to amplify in very dramatic ways. 1985 was one of the most dramatic earthquakes. It's called the Mexico City earthquakes. It was not in Mexico, it was way offshore, but waves amplified a lot when they go in that lake, kind of like a bathtub. And so because this is subsiding and compressing, the earth is changing seismically as well, in the sense of, excuse me, the seismic wave speed, the speed at which waves travel through this material is changing significantly over time. And so here we have an example of 25 years, given one site. It's actually a very long time series for seismology. Most of the networks have expanded in like 2005 and beyond. So we have a continuous 25 years of record since 1995 with some data gaps. And you can see this non-scaled time series of this velocity changing over time. There is a little bit of weak seasonal fluctuations, and I think that's because I was told by a grad student there's no weather there. It's all the same. So we have some weak seasonality, but also this long-term trend of increase, and we found like 4% of change in 25 years. Now, this change in velocity over 25 years, it's the lifetime of building code have to be updated, because if we change the type of soil, we have to change also the type of basically building response that we need to design for in the case of an earthquake. We also noticed, if you remember in 2017, there was a nearby earthquake that also caused damage, and we can see these effects of a sudden drop in seismic velocities. To the right, we're mapping this slope and these rates, and the dark colors show a stronger long-term trend of these changes, and they're correlated with the annual average basin subsidence. And the more within the basin, the more inside the basin you are, the greater the subsidence is also the greatest change in the seismic velocities. But anyway, these are timescales that building codes really have to adapt. Just wanted to, this could be a lot, but just wanted to tell you we're also doing that on volcanoes now, this kind of time scale. So I'll show you briefly. I know this was kind of a lot of overview, but these changes in velocity we're doing in Mount St. Helens, where we're trying to capture the 2004 eruption and a precursory. Can we predict it? And it's a very noisy measurement, but what we're seeing a lot of long-term trends as well, seasonality due to the snow load, precipitation, but we're trying to investigate what is causing this long-term trend in the Mount St. Helens. So trying to start deploying this in all volcanoes is what we're trying to do. Okay, so I covered a lot of topics. So I just wanted to conclude is really seismic time series contain a lot of information beyond just earthquakes. We have earthquakes, we have atmospheric events, we can sense the ocean, we can listen to the wildlife, we can sense soil science and critical zone science, we can sense and listen to hydrology, which I've not touched here. And kind of to enable this kind of science, the research group here is to really find better ways to extract information, both with a better cyber infrastructure, better coding algorithms, but also smarter ways to find like what are the new features in the data that can tell us about these processes. So I would say that in our group, we tend to do a lot of discovery-driven science, even though sometimes, I mean, we all have hypothesis-driven science, but I feel like, coming to this new place with so much data, so many natural systems to explore, Brenna, we've been focusing a lot on that discovery. So I want you to try to replicate the style maybe of eScience in enabling a lot of this. So we really try to promote it. I'm learning a lot from eScience, and so I'm so grateful to working with all of you. But thanks to you, my students are doing a really amazing job, and we're learning how to code Python as an object-oriented language, which I had ignored until now. So thanks, Carlos. But anyway, I just wanted to point out all of our science and ideas are actually online. I don't think I'll get scooped because it's hard work anyway. But so thank you for listening, and thanks eScience for really enabling a lot of that.
Thank you very much, Maureen, for this wonderful journey through your research and like potential new possibilities of research. We have a question in the Q&A box. I would like to read it out to you for the slides part. I'm thinking yes. Landslides. Have you tried validating your predictions with landslide inventories?
Well, so that's a good question. And the reason is we have not, but these people have. This is a collection of events that have been ground truthed. And they come often with validation that are DEMs, INSAR, time-lapse imagery, and validation from local people. So this is what I'm trying to use is, given these ground truth measurements, can we now go to the Pacific Northwest unlabeled data and try to classify within that? There's going to be some logical things like it should be correlated with slope. It should be correlated also with topography, and maybe it should be correlated with a time where it was wet. But these are I use this small ground truth data to try to explore what it would be in our unlabeled data. But if there were opportunities to here collaborate to find more ground truth data, I know there's a lot of slow landslides and fast landslides. I came from the earthquake perspective, so I'm happy to learn more about ways to validate this. And what I think would be great is seismology has this super cool time resolution, continuous time resolution. What we don't have is space. We're starting to have it with new sensors, but I think the next step would be to match these with imagery, geospatial imagery. and the match of time series and spatial data will really get us to locating the events and doing more process based investigations. So please contact me if you want to help us do that.
Well, thank you for that. Maybe I'll ask a question that interests me.
Yes, please.
You did mention a connection with hydrology, and I'm interested in interdisciplinary research as well, and the possibilities that all these data sets open for interdisciplinary research. And I was wondering if you could elaborate at least on that side of things.
Mm-hmm. Yeah, so you've seen that we've compared with subsurface hydrology with these LWE, WE measurements of overall content of water. But the surface hydrology I did not show, but basically if you go and walk next to a river, in the spring, you will hear the river with sounds, right? This sound is actually coupled also to the subsurface, and you can record them at on seismometers. And the amplitude of that sound and the frequency content is going to be governed by the discharge, the flow, and grain size at the bottom and turbulence in the flow. And so you can actually turn seismometers are kind of like bedload transport sensors or discharge sensor. There's some crude approximation to do, and they still need to have ground truth validation with actual hydrology measurements, but there's a ton of opportunities to do that kind of surface hydrology sensing where there are seismometers. You can even listen to salmon spawning. Like it's like there's a lot of noise within the water that actually can also be from the fish that you can listen to. There's a cool paper from a group in Germany that actually looked at the Washington salmon activities. Of course, whales are not, but yeah, the hydrology, it's there's a lot of when it's loud, seismometers won't get it.
Excellent. Thank you for your presentation today. That was really great. I think we can conclude here, and we'll see you next time.
Thank you so much. Enjoy the nice weather.
Thank you.
Thanks, Nicoletta.